Hello everyone. My name is Pratyara Chaudhary, and today I am presenting my project on enhancement of MobileNetV2 CBAM for UAV-based fire detection. Uh, so, as we know, forest fires are a growing global crisis. Traditional detection methods like satellites are often too slow, and human patrols are dangerous. Uh, so Unmanned aerial vehicles or UAVs offer a rapid solution, but they require artificial intelligence. We all know that. And that should be fast and accurate. So, the core problem we face is the reliability. The lightweight models deployable on drones often struggle to distinguish between actual fire and smoke or fog, leading to high false alarm rates. My objective for this project was to build a system that solves this specific limitation. So, I selected the research paper titled A Lightweight CNN Model for UAV-based image classification, published in Soft Computing 2025. This paper proposed using MobileNet V2 for its efficiency, as you can see. However, upon critical review, I identified a significant research gap on page 14. Uh, on page 14, the author explicitly admit most error-prone fire images contain strong smoke. It is necessary to further improve the model for complex scenes. So this became the foundation of my work. My research questions were, can we teach the model to ignore smoke and focus only on the flame? Can we bridge domain gap between clean training data and the real world smoky fires? So, uh, to answer these questions, I proposed a unique architecture, MobileNet V2 CBAM. Let me explain how it works. At first, the data processing. I utilized flame dataset for aerial imagery. I applied resizing to 224 across 224 for consistency, normalization using ImageNet standards, augmentation like rotation and flipping to improve robustness. Uh, the model MobileNet V2 plus CBAM. I chose MobileNet V2 as the backbone because of its inverted residual blocks, which are perfect for edge devices like drones. However, I enhanced it with CBAM. So the convolution block attention module, the full form it is. CBAM works in two steps here. First, the channel attention. It asks what is the feature helping the model to prioritize fire texture over leaf texture. Second, the spatial attention. It asks where is the fire, effectively creating a spotlight on the flame and suppressing the surroundings like smoke. Now let's look at the technical implementation. Uh, I built this end-to-end system using PyTorch for the model, Fast API for the backend, and Next.js for the dashboard. So this is the training script. After running this training script, we will see something like this. I have picked five epochs to train the model with the data, the mobile net v2. So we can take more epochs if we need if we think that the accuracy is not as per we wanted. So we can take more more trials, more iterations. This is using CUDA, so my GPU. In my case, my CPU is not so powerful. That's why I am using GPU for acceleration. But this training also can be done with the CPU. It will take a time, but it can be done with a decent CPU. You can see the Next.js is using as a front end for this dashboard section. I am using First API for the backend. As you can see, if we import a image, It will detect it is fire or not. So this is the API endpoint for prediction, and we can see that this has resulted fire. If we just import something not on the fire, not on fire, then it will result no fire, as you can see. So, mm, so this is the API, and this is the dashboard. From here, we can select the same thing we can do from here. So let me demonstrate another thing. Let me just choose a better image to demonstrate, which involves a lot of smoke, like this one. So if we detect this one, this detects fire. And how it detects the fire? You can see it classifies the fire using the heat map, and it classifies the fire texture only, not the smoke, not the surroundings. So that's why it can detect the fire easily. And you can see this is the confidence score, which is 100%. So it is high confidence, and it is the GradCam heat map. So that's it. So to rigorously test my solution, I performed a comparative analysis using secondary dataset from Kaggle, representing a domain shift. So the baseline, when I ran the standard MobileNetV2, it failed catastrophically on the smoky dataset, achieving only 48.4% accuracy. It was guessing. The proposed solution. After implementing my domain adaptation strategy, where I merged diverse smoky samples into the training pipeline, the accuracy jumped to 95.8%. So comparing, we can get the baseline was 48%, 48.4%, which we can consider failed, and ours was the final product was 95.8% accuracy. So this is a 47% improvement, which validates that my approach successfully bridged the generalization gap found in the literature in the research paper of Springer. So, so in conclusion, I have successfully reproduced a state-of-the-art lightweight model, identified a critical flaw regarding smoke, solved it using attention mechanisms and domain adaptation. So Uh, for future work, I recommend porting this model to an NVIDIA Jetson Nano using TensorRT for fully autonomous drone deployment. I also think expanding the dataset to include nighttime fire imagery, it will further improve our solution because fire can happen at nights also. So we have to take measures about that. So that's it for my project. A little improvement on existing research paper. Thank you for your time.